Alright, so welcome to Lepton Triptych 1, Part 3. In this video, we're going to cover lepton fields and specifically their classifications within this, which is the most important result from this paper. But first, I would like to cover an errata an error I made in the last video where I said that this rho naught squared gives you minus this idempotent right here. Actually, it gives you minus the box. Which is a different idempotent that's defined or the box is defined as 1 minus the other idempotent. But, okay, if you remember last video, we have the spinor space, which was defined as any element of the geometric algebra times box. But we showed how we could consider only a subalgebra, G2, of the full geometric algebra, G4, and consider just elements of that, and any element of this form could be rewritten as A plus B box and then this little b one. So now we can find lepton fields by classifying them. So suppose we have some C, which is implicitly here defined as C times this box. So it's in the spin space. And we're going to consider instantaneous and infinitesimal transformations under U2. I say infinitesimal because when you take an infinitesimal transformation, the only contribution comes from identity and instantaneous transformation. So let's suppose we have some value significantly less than 1, and then we define some rotate or some transformation in our U2 such that we take an exponential of 1/2 this infinitesimal value times rho, where rho was defined in our first video as just being, or I'll just go back up. I'll just go back up to the definition. This is rho right here. Or this is for SU2, but if you're doing U2, then you go from J equals 0 to 3 instead. So then we look at the transformations here. So if it's infinitesimal, we can expand this. We can expand this summation here, which is just the Taylor expansion. And we're going to just get the first term. That's going to be everything to the power of 0, so just 1. And then plus 1/2 epsilon rho. And then the next term will be plus 1/3 factorial epsilon squared rho squared, and we'll keep going. However, if you have an infinitesimal value epsilon, then all the terms here are going to vanish. They're going to go to 0. And so we can say that this is, in practice, equal to just 1 plus 1/2 epsilon rho here. So this is the infinitesimal transformation that we will be using. And you can see that what I mean by instantaneous is that you can think of the total transformation as a linear sum of identity, then a small transformation, then a small transformation applied twice, and then it'll be 3 times. But in the infinitesimal limit, only the instantaneous contribution is going to be at play. All right. Now let's we'll be using to classify. What I mean by classify an object of spin space is we're going to compute the commutator of it in something called the Cartan subalgebra. So let me define a Cartan subalgebra real quick. It is, or rather, I'll just do this. Say a Cartan subalgebra where we have the definition of it is H, and it is a subset of a Lie algebra L, is a subset such that for all L in L and for all A in H, then we have if the commutator of L and A is in the Cartan subalgebra, then we have that L must be in H. And so effectively, what this is saying is that a Cartan subalgebra is a subalgebra such that only elements of the subalgebra stay in the subalgebra. It's not like an ideal where if I take an element of a Lie algebra and then I multiply it times an ideal, it stays in the ideal. This is different. And so what we're going to want to do here is we're going to consider the commutator. We're going to take the elements of our spin space here and then put them into this L here and consider the commutation with A, where A will be in the Cartan subalgebra. I'm not going to prove what the Cartan subalgebra is, but elements of the Cartan subalgebra in our case the Cartan subalgebra is the span over row naught and row 3. So in our case, this is what H is. So now let's consider the infinitesimal rotation. So this will motivate why we use the commutator. Okay. So now we have U epsilon C U epsilon reverse, and this is going to be the same as 1, or remember, approximately, same as 1 plus 1/2 epsilon rho C, and then 1 minus 1/2 epsilon rho. And we're going to get a term of C, and then plus epsilon 1/2, and we'll get rho C minus C rho, which is just the same as C plus epsilon, then the commutator of rho with C. So you can see that when you consider the infinitesimal transformation, the only contributing term is this instantaneous transformation. And these elements rho, we're now going to restrict. So rho can be R0, R1, R2, or R3. We're going to restrict to R0 and R3, or rho 0 and rho 3. so that we can just consider the Cartan subalgebra. Alrighty, so we have that. Now, let's just recall a few facts. I'm going to put them in a box. Rho naught is just the sum of these bivectors b1, b2. And rho 3 is b1 minus b2. Also, b sub j is just e1, e2, or e1 bar, or ej, e bar sub j. Alrighty, so we have these facts. Now in electroweak theory, what do you call it? In electroweak theory, the generators of the Cartan subalgebra H, which recall these are rho naught and rho 3, are respectively hypercharge, and hypercharge is usually written here with a factor of 1/2 y, and isospin. So what this means is that rho naught is the hypercharge, and rho 3 is the isospin. And it's also known that electric charge is Q equal to 1/2 hypercharge plus plus the isospin. So we get that Q is equal to rho naught plus rho 3, which is going to be 1/2 b1 plus b2 plus b1 minus b2, which is just b1. So this right here, we now have our definitions for hypercharge, isospin, and electric charge. Now what we're going to do is we're going to look for things that are invariant under rotations or instantaneous rotations by this. So what you can think about is that if you apply an instantaneous rotation of something with hypercharge and it doesn't change, then that's a value that's something that is that takes a value of hypercharge. If there's something that doesn't change under isospin, it's something that takes a value of isospin. And likewise, say something takes values under these two, and that gives a separate result that it takes value under here, then you get electric charge. So all these charges are really just things that are invariant under these instantaneous rotations. So what does that mean? It means that we look for eigenvalues. Specifically, we take rho, whatever our generator is, we take psi, which is taken from up here. And then we look for values that are like this, psi, and then B1, where lambda is a real number. And so this is the eigenvalue equation. And in traditional Lie theory, usually you have this, but it's then equal to what do you call it, lambda psi, and then you'll have the imaginary unit I here. But as covered in the previous videos, the bivector B1 covers the role of the imaginary unit. So we're looking for eigenvalues here. And I'm going to just cover 4 cases, the 4 cases of the paper, because those 4 cases will correspond to particle fields. Let's go over this. So the 4 cases in the paper. We consider 4 cases. And that is 1, 2, 3, 4. The first one we have is C1. Then we have C2, C3, and C4. And it's alpha plus beta B1. Here where alpha, beta are real numbers. And then C2 is, I also forgot to mention all of this times box. Then C2 is E1 times alpha plus beta B1 box. Then C3 is E2, alpha plus beta B1 box. And C4 is E12, alpha plus beta B1 box. So these are the 4 cases. And you can see the G2 structure here of these elements. Namely the, what you call it? There should be a box there, but namely you see the, this is 1 times 1 here on the left. Okay, 1, then you have E1, then you have E2, and E12. These are the bases for G2. So we have G2. Now we consider all of the eigenvalues for all of these 4 cases under rho naught, rho 3, and then B1. And that will be looking at the hypercharge values, the isospin values, and the electric charge values. I will calculate this explicitly for all 3 cases for Psi1. And then for Psi2, I'll only do 1 case because all of the rest of them follow from it. And then I'll summarize. So for 1, let's consider hypercharge. I'll do this. We have rho naught with alpha box plus beta box B1. Well, rho naught commutes with rho, or with box, and B1 commutes with rho naught. So why does this happen specifically? It's well, first remember that B1 B2 equals B2 B1, so these commute, and rho naught equals 1/2 B1 plus B2, and and box is equal to 1/2 1 minus b1 b2. And so this rho naught, because rho naught is comprised of b1s and b2s and they commute, rho naught must commute with box and must commute with b1. So this whole commutator must be 0. And likewise, it actually ends up being the exact same reasoning for isospin. This also ends up being 0. And this means that electric charge is also also 0. Like so. Now, let's go to a less trivial case, and that is for the hypercharge of the C2 field. So this field right here. So rho naught. Then E1 alpha, or I'll just write it like this, alpha E1 box plus beta, and then recall B1 is equal to E1 E2, or sorry, E1 bar, which implies that, which implies that E1 B1 is equal to E1 bar. So we get E1 bar box. And now we need to use two other properties. That is that rho naught E1 is equal to minus E1 rho 3, and rho naught let's see, E1 bar is equal to I accidentally on my paper I wrote E2 in a few places on accident, so I'm looking over it for the moment. Okay. Gives E1 bar rho 3. Now it should also give minus 1 E bar rho 3. Hang on, so then if it gives minus there, okay. I hate having typos in my notes because it just throws me off in the video. I believe, yes. So, okay. So yeah, we have this. So these simplify to, I'm now going to use the definition of the commutator. And we're going to have rho naught alpha E1. And I'm going to move box all the way outside. Then plus beta E1 bar. Then it'll be minus alpha E1 plus beta E1 bar, and then rho naught. Then the box will be out here. Then we get, or actually, we're going to get 1/2. Then be minus alpha E1 plus beta E1 bar, and I'm going to do 1/4, and then it becomes B1 minus B3, or B2. I'm going to absorb this minus sign here, so that's going to become B2 minus B1, then minus alpha E1 plus beta E1 bar, and then beta, or B1 plus B2 box. And call it this term, this, and this will combine. This, and this will also combine. Wait, hang on. So I'll just multiply this out. 1/4. I'm going to get alpha E1 B2 plus alpha E1 minus B1, and then plus beta E1 bar B2 minus beta E1 bar B1 minus alpha epsilon 1 B1 minus alpha, or E1 B2, then minus beta E1 bar B1 minus beta E1 bar B2, all of this times box. And this term will cancel with this term. This term will add with this term. So let me just mark these. So this will vanish. This will vanish. This will vanish right here with this. So we're just left with 1, 2, 3, 4 terms. So this is going to just be 1/4. It's going to be minus 2 times alpha E1 B1 minus 2 times beta E1 bar B1, and then box. Let's put this higher. So 1/2 minus 1/2, and then I can factor the B box back in and factor the E1 back out, so I get E1 alpha box plus beta box B1, or actually, hang on, was it times B1 here? Yeah, it was. Oh, I see. Yeah. I should have no B1 here. No, I should. Okay. It's there. B1, and then there's going to be a B1 out here. And this implies that the eigenvalue is minus 1/2. Okay. I feel like I made an algebra mistake throughout this derivation, but I gave the correct result. I just wish that I hadn't had that error in my notation earlier. So 1/2 C2 B1. So this value right here. Likewise, if we do this for isospin, we get row 3. I'm just going to write C2, and this is going to give us also 1/2 C2, B1, minus 1 half B1. And then for Q, if we take B1 with C2, then we get minus 1. Or minus 1 is just C2, B1, like so. And we can continue doing this for all the other cases. I'm going to just write them like so. If we compute the same values, here, then we'll end up with a minus 1 half C3B1 here, a plus 1 half C3B1, and then a 0. And then here we'll end up with a minus C4, then a 0, and then a minus C4B1 here, if we compute these. So now let's make a table. Kind of a bad table, but here we're going to have our values of C. Here we're going to have our hypercharge values. Here we're going to have our isospin. Here our electric charge. And then this will be the lepton field. So for our C1 equal to alpha plus beta B1 box, and then our C2 equal to E1 alpha plus B1 or beta 1 box, C3 equal to E2 alpha, plus beta B1 box, C4 equal to E12 alpha plus beta B1 box. So these are all of our fields. We saw that this took a 0, then a minus 1 half, then a minus 1 half, and then a 0, then this took a minus 1. For isospin, this took 0, this took minus 1 half, this took positive 1 half, this took 0. For charge, this took 0, this took minus 1, this took 0, this took minus 1. And so we can see that the fields here correspond to, I'm writing purple, something that doesn't interact. First, if this has 0 hypercharge, 0 isospin, 0 electric charge, it means it just doesn't interact at all, which might as well not exist. And so that's what we call a right-handed neutrino field, because we don't observe those. And recent observations have actually led to the conclusion that they most likely do not exist. Then for C2, something that has values in both and has a charge of -1. This here is a left-handed electron field. Then here we have something that does interact with the electroweak force, but doesn't interact with the electric force. And so this is a left-handed neutrino. And then here we have something that must be an electron, but it's right-handed. And notice that we have objects that are right or left-handed in terms of traditional particle physics chirality, based off of whether or not the spinner is even or odd grade. So even grade, right-handed, left-handed, because they are odd grade. Yeah, this is the major result of the paper, and it's how lepton fields can come out of the structure of G4.